So I'll skip the introduction what Facebook is. Probably some people know already about it. But what I'm going to talk about today is, and me and Harrison, is about our small data platform. It's like don't take it wrong. Small doesn't mean the volume of the data. It means that each of these items are individually accessible and available for all this real-time interface of Facebook users. And it's essentially your user-facing data storage and user-produced data storage. The scale, yeah, we probably talk about large numbers here. The number of queries here is what hits the database backend. We have caching layers that actually reduce that by from billions of data accesses a second to just 50 million queries a second to the MySQL backend itself. And obviously there are other numbers where the number of rows and objects read from a database can be a few billions a second, but when backup cycle comes in, it's much bigger than that. And we love our backups. Being able to restore is important. The other thing is the actual churn and additional data that flows into the system is everything what users do, and that's 10 million a second, right? Not that small. The other thing is we cannot really build that as an in-memory storage. The amount of data is in petabytes. So we really have to think about how to structure the I/O and how to handle the I/O and how to build a scalable system, which in the end handles up to 40 million I/O operations a second. And even network traffics are in hundreds of gigabits, and all that is actually happening at kind of millisecond-ish response times. So the main if you did some of the math, you'd see that responses are on average kilobyte, few kilobytes, and a few rows, but they're such intensity of the system and it all flows into just serving all the data for our users, which is has of course the hierarchies and has interesting implications once you look at it. When you look at the Facebook page, you don't just see your own profile. It was in 2004, but now it's a bit different. Actually, see a flow of various events and something like comments and other things associated with those events. And then there's also these tiny pieces of data comment likes or page likes. And all of that, what you see is not just the data that is pulled from database. It's all what has been filtered and passed through the social context and your circles, social connections, and filtered. So you will see people you care about more in all the page around you. And all of these things, they can result in tens of thousands of data accesses from a single page view. And this category is of course the graph itself is so what is social graph? It's quite often from large main objects like pages, applications, and users, and then you have relationships between them, and it goes to these smaller and smaller there can be billions of photos a billion photos uploaded over a weekend, and all of these interactions with these objects form this enormous graph that may have has trillions of objects that Ravi talked about from an analytics perspective. And the way we look at it, of course, we try to cheat as much as possible. This whole thing that we serve. Even we have interesting products like Timeline, where you can go and watch your history, and you can go and look at photo albums and all different historical content that is on Facebook and is accessible from every click for all these users. We still have our major pattern is really up to date, really close proximity, social reach. Objects come and go. People comment usually on the new stuff, and you don't really go and write comments unless it's an anniversary of something, right? So, and the other thing is it's all global. We have users in Asia, we have users in Europe, we have users in Americas. So it's all of that has to be accessible and reachable from data centers that are in the world. And this gets us to this really not just storage, but also data distribution challenge that we have to deal with. The other thing that we have is a really fast-growing and really fast-moving development team. The actual platform that we have comes up with the idea that development teams don't have to wait for the data teams to really predefine what they should be doing. Development team can go and build new product, and we'll start noticing it when it reaches maybe 10, maybe 100 million users. Then we start thinking about how to better optimize it. So this is like the moving fast of development has is different from actually designing such a system. Such a system is relatively like generic framework for anyone to build what they want for this like social world. We have we have some simulations. There is a published Sigmod paper on Linkbench, which kind of tries to point out what kind of operations, what kind of data locality and distribution you would observe if you would have to build a system of a larger scale like this. It's more used now for like smaller node comparisons, but it can be expanded to relatively large simulated access. At the core stack, obviously we have caches that everyone says that we should not have, and instead have anti-caching or whatever. And we have MySQL, and we have again Tau. But the major thing is like all of these components that are there, they have so many different constraints that they have to fit into. If we would not cache next to a web server, the network would melt because of, you don't want to suddenly start sending hundreds of gigabits of traffic over the Atlantic just because you forgot to put a cache somewhere out there, right? And obviously, it's already from database. If you extrapolate that, if we have actually dealing with billions of requests at the cache layer, the traffic inside the data center can be much, much bigger, and especially within the clusters where the systems are way, way more interconnected. And even then, like cache cannot have everything covered. There is like historical access. There are pointwise checks that are important for various operations. So I really have to be able to go and see, do I really like Justin Bieber? Even that could have happened 5 years ago, right? Well, did anyone? No, it's too young. But anyway, and then when we have to build on top of the stack and add sub-publishing for other systems which want to tie into the graph and be able to send that data into analytic systems or indexing systems for different operations on the graph, not just simple accessing of associations and objects. And we obviously had to work, even Memcached, when we took the open source version of Memcached, we had to add lots of performance improvements and enhancements, like remove the global mutex at least, and add threads and UDP protocol and lots of other extensions that would allow us to have millions, up to 1 million requests or like more per node. So there is a relatively interesting development in all of these, and you can follow some of both Memcache and Tau are published papers and how we do the acceleration beyond the data store. But the data store itself has been an interesting story for us. As Jeremy said, we actually have to have in-house branch just to be able to really adapt it to our needs and push forward initiatives that the general business forces around don't push Oracle to do yet. And so it's all open source and public right now. We really think about some of the important things for us are how to make it work under our constraints. We never really cared about how fast the QPS rate for in-memory. Our data store is not in memory. The machines that are able to handle the in-memory data patterns have to be sitting somewhere next to the web server and it doesn't have to hit the database. It's already a big cost. The database, though, has to handle all the persistency on whatever hardware it has. So if it's disks, it has to care about IOPS. If it's flash, it has to care about space. And so we really had significant effort in improving such parts of MySQL as data compression in OLTP, because that's a significant cost saving. And we actually care about cost. Like yesterday, I was contemplating, there were multiple mentions that if you can just over-provision and throw hardware at the problem, in the industry, it's so easy. It's kind of odd. We thought in the industry, that's how we thought about scientific systems for a while. And these conferences actually allow us to kind of better understand this. It's like all of us are working on really fun problems. So it's right now, we are trying to upgrade to MySQL 5.6, not enabling all the features yet, but it's an interesting work. We find issues with once you throw a small subset of testing machines, few thousand, and you start looking how they perform, you actually start seeing interesting issues. So We simplify things a lot. Like at the moment, we don't try to do any like really fancy multi-master, or like we just have single master. We try to work on good durability and failover, and like really have decent transactional operation on those individual nodes. Maybe we don't have like a full consistency across the whole graph, but we are really confident how our individual nodes perform and respond to any kind of situation. And we have, as I mentioned, we are global. We have been using standard MySQL replication. There were ideas maybe we should change that to some more complicated designs, but it's like MySQL replication is relatively easy to understand. It's statement-based. You understand what kind of work is going to be done, and you can like wrap your head around it without too much sweating. We don't do, as I said, don't do multi-master. It's just simply, if you look at it, yes, we could deploy some eventual consistency, but it's just difficult to go and to talk to all these different engineering teams around it. By the way, from now on, you have to think that this data might not be the data you will see in a millisecond, right? Like it's the actual programming methodologies around data sets shift a lot when you don't have just a simple, consistent concept, even if it means that you have to move some of your operations closer to the database master. As I'll show later, we don't even store local replica of data in a data center if a node goes down for our major data set. If a node goes down in a data center, we go to another data center. And that also means that we can have to take speed of light hit. I don't know how many physicists will fix that for us someday, but just adding 20 milliseconds to request just because a node is down, in the end, it's just statistics for us. When you have to assemble 1,000 requests and some of them are slow, while you're assembling those fast ones, the slow ones can obviously trickle in, and you'll still render the page in relatively decent time. So even those latency, even we have 1 millisecond latency, even this allows, we actually had to build systems and methodologies like concurrent programming in PHP, who thought, right? So we had to do all that just to not mask the latencies, but simply to allow us to tolerate and be able to work on different parts of the page while data is getting assembled, because we are such a data-intensive process, just to show some kittens, right? So we worked on things like replication language Jeremy mentioned. It's an interesting issue, especially in disk-based systems. You have usually 8 disks in a machine, but a single thread will usually use just one, because when you're reading a page from data storage, it's like that's all you can do. You have to wait before you know what you'll do next. So that was, and only 1 out of 8 disks or 16 disks is being used, and even though you could, if you queue like 100 parallel requests to your RAID system, its efficiency improves. So we really had to work on things like prefetching of replication. We worked with Percona to add a feature called fake changes, so actually run statements without actually running them. It's not that difficult as some of the physics concepts, but we actually were able to get our replication performance nearly to the parallel replication speeds years before parallel replication is usable in production. We have some charts. So it's kind of, obviously, if you build a stack that has more and more services and more consumers of data in different kind, and you build pub subsystems, we end up with having this kind of, this is a basic diagram where everything is centered around the data shipment by replication, but there are kind of out-of-bounds channels, and when someone writes the data, it produces the pub sub events that can go either directly from local data center, or get shipped by MySQL into another data center and pulled out there. And that's kind of the really basic global map, where if a master, any node in a master region dies, we switch to alternative master region, and those are generally like the regions with most central location in the overall data center map and closest to each other, so that the latency of going to the master is not as high as crossing the ocean, or especially if some cable gets cut by some fishing trawler. And even then, the interesting thing is when you go to really large scale, really interesting physical constraints start appearing. For example, the buildings cannot be like really, really, really large, right? You have to build multiple buildings usually to I mean, you can build like Boeing assembly kind of factory, but it's not, but then just pulling in power, building out like network topology in there. Even if you are building a single data center region, like in Prineville we have multiple buildings, there are still, even those large buildings get divided into smaller units to make network manageable. So you start thinking in terms of like you partition stuff and think about clusters, and each of these clusters has its own separate kind of data caching domain. And whenever people talk about how much memory is spent to cache the database, it's not about that. It's just about shifting the data to these like tiny, relatively tiny clusters next to the web servers that deal with the hottest objects. Because when millions of people suddenly start commenting on some picture of 4 more years or something like that, you don't really want that to melt immediately all around, right? So, and in here, Tau is write-through cache for us. So it has its own topology, and like followers can talk to leaders that are sitting next to the database. And application server can decide either to go to database directly, to go to and look at memcache first, which is if it uses memcache, or for most of the graph operations, it goes through Tau, which maintains a head of list, a head of association, and some object properties in memory, and doesn't have to go to the database for that request. And that is essentially we don't have to work as much on things like row cache within the database, because we have these externally, and adding just internally would overlap. So the concepts of anti-caching actually are not really applicable here. And the MySQL, Jeremy told, he said lots of things that I will probably repeating, but what we look at quite often is how efficient is MySQL at serving the data problems that we deal with. In memory efficiency or I/O efficiency, especially with InnoDB compression, is way beyond lots of other things. Even then, like the data clustering properties within the server mean that your neighboring records will be on the same page. They will not be scattered all over, like with kind of more heapish storages. And on top of that, just because we have, even though we can run the website with 4 SQL queries, or maybe 5 of them, it's difficult to count that much. The additional ETL workloads and backups and introspection and recovery and migrations, just having SQL framework on top of this kind of data set is really, really, really useful for us. And we kind of in these years, especially after working on MySQL, and then our database engineering people worked at Google, and so we kind of start understanding what the performance properties are and how not to make some of the mistakes. So it's good. We have engineering team who are working on improving, and we fix problems all over in different places where they're from file system handling to in-memory system. Like we notice, we fix, obviously, but we always share these things and they get into upstream eventually. So it's like generally MySQL has not been too frustrating for us to deal with. So Harrison will talk a bit more about the logical side of and other sides of the database. The green button.
So my name is Harrison Fisk. I'm manage the data performance team at Facebook. So I'm going to talk about a couple of different topics around our database infrastructure. The first thing I'm going to talk about is sharding. So I should have probably coordinated a bit more with Jeremy, since the first thing he said was range sharding is bad, and that's what we use. But sharding, I don't think, is actually that hard of a problem. It's relatively easy. It is easy to get wrong as well. But in our scenario, it's pretty straightforward. So what we do is we assign users to a shard. So when you sign up for Facebook, you're given and you're assigned to an internal shard. Now, each shard is given a range of IDs. In this case, a very large range, several billion values that can be used on the shard. And then the shard generates its own IDs using auto increments. Another thing Jeremy said is really bad. He stands by his positions. We'll have to debate this later. And so basically, we have lots and lots and lots of these shards. And there's always a growing number of them. So we'll always have new people signing up for Facebook, hopefully. And as we do that, we'll create more and more shards. Now, the interesting thing where I think Jeremy probably sees the issues is we actually put lots and lots of shards per database. So rather than saying, OK, there's one shard, one database, one server, instead we'll put a bunch of shards on a single instance, and we actually put a bunch of instances possibly on a single host. So the idea here is we get flexibility because there's all of these little shards to basically move things around and in order to balance things much better. Other properties that we try for, first is data is co-located with previous values. So when someone says, hey, I want to create a new photo object, normally that will go with the owner's shard. So all of your photos exist on the same shard as yours. That allows us to do things like within a shard, you can do joins, you can do transactions, and we actually do both of those things. Where you get into issues is cross shards. So when you have distributed transaction type things, we kind of punt on this. Basically, we do best effort, and then we have asynchronous cleanup processes that deal with failures later on. And that's basically our sharding. So as I said, the shard placement is actually an important thing for us in figuring out how to balance things. So because we have so many shards, we're able to balance based on things like size. So certain shards will be very popular. Things like Farmville, is a huge Facebook application, lots of comments, lots of things all being generated in their shard. So we can move that shard off to different hosts because it grows faster than some of the other shards. All right, so that's our basic way we do sharding. Again, it's pretty easy, I think. We've never had to reshard, and we hope we never have to, because resharding is the hard part. But we hopefully can avoid that by creating lots of little shards instead. So the next thing we're going to talk about is data center automation. So this is actually the main thing that our database operations team does. Technically, they call themselves DBAs, but really they're mostly automation technicians. So they've created a system that we call MySQL Pool Scanner. We published some blog posts and discussed this some, but basically the idea is when you're dealing with the number of servers we have, many thousands of servers, there's nothing that you can do manually. Everything has to basically be 100% automated. So we have this centralized system we created called MySQL Pool Scanner. There are some other ones, like there's open source ones, like there's one called JetPants that Tumblr open sourced, which handles a lot of similar things. But the idea is you need frameworks around MySQL in order to scale to this largest thing. So MySQL Pool Scanner, as its basics, is basically a server state machine. So basically it knows, OK, what state is this machine in? Is it production? Is it in repair? Does it need to be reimaged? Does it have failing hardware? All of these sorts of things. And it will then transition the machines between those states. So it does things like server bootstrap. So when we're bringing up a new data center or we're getting in new shipments of hardware, it does everything from verifying the hardware works, to imaging, to installing MySQL, to configuring for doing basic tests. Then we do things like hardware failure detection. So hardware fails a lot when you're dealing with so many thousands of machines. And so it tries to detect disk failures, RAID batteries, flash cards, CPU, RAM problems, all of those sorts of things. So it ties into all the various diagnostics to try to even detect these before they become bigger problems. ECC errors, things like that, it'll replace based on those. It also does things like schema deployment. So again, when you're dealing with so many shards, you have lots of copies of the same schema, and we need to deploy these new schemas out there. So these are things like adding new columns, adding indexes, changing things, adding tables, dropping tables, all those sorts of operations done at a very, very large scale. And this gets a little more complex than it seems because of the fact that at any given time, servers may be down, unavailable, and then come back later. So it has to do these verifications later on to make sure the schema change is really out to everywhere across the entire fleet. Capacity management and shard instance and placement. So this will do things like, hey, I noticed that we're starting to run out of disk, so maybe we should move some shards over here. It'll do things like based on load, we're working on right now to have it do some better management based on load as well, to notice, hey, this is a very hot shard for some reason. Maybe we should move that off other places. And we're working to integrate all of these sorts of DBA type things in order to make it much more automatic. So the next thing I'm going to talk about is hardware. So within a data center, of course, we have hardware. So the biggest problem we have with hardware, and the biggest bane of everything, is the fact we have many generations of hardware. So when you see all these clustering and all these different technologies, most of them presume that all these nodes are roughly equal. Well, in our case, we have all these generations of hardware. Why? Well, we bought hardware 3-4 years ago. We bought hardware 2 years ago. We bought some now. And we're continuing to buy new ones in the future. And so within this, we have data centers that even have kind of these different generations. So we have some pure disk, a little bit left. There's not a lot of those. We've actually replaced most of those. So what did we replace them with? Well, we replaced them with first our flash cache technology. So this is where you have large storage. So you have disk-based, where you have a flash accelerator in order to speed that up. And then we also have pure flash. So we have pure flash, where basically you have only flash storage. There's no disk at all within the system. These all have different characteristics and have different importances. So like pure flash, compression is super, super important. Why? Because there's only so much flash you can put into a system. So we spend a lot of time space optimizing MySQL. For flash cache, IOPS is still super important. So we'll spend a lot of time trying to reduce the IOPS. The same thing when you're dealing with pure disk. Pure disk also has IOP constraints, so you spend a lot of time optimizing for all of these different aspects. And finally, the last thing that's really cool at Facebook is we have open compute. So basically, we get to actually make our own hardware now. So we actually get to work with our hardware teams to figure out what do we need for a database server. Can we remove these bits? Can we add these bits? And so on. It helps reduce the efficiency, but it also gives us access to all sorts of kind of bleeding edge things that we can play with all of these new things. So we've been using Flash actually for many years now. And so we're really good at dealing with Flash and knowing the constraints and how to manage that and so on. So that's basically our brief overview of how we use MySQL and our various technologies around it. Do we have any questions?
We really encourage questions.
Yes, thank you very much.
Thank you.
I'm sure there are questions. It's just a question where.
I have a quick question. Whenever you mention something like millions of queries per second and so on, are you referring to queries hitting the database or hitting the cache?
Cache is billions, database is like tens of millions.
Yeah. Many billions.
Okay. Does Wormhole have its own durability mechanisms? Do you rely on MySQL? And if it has its own durability mechanism, does it also have its own network overlay?
It's essentially relying on MySQL right now. It's essentially a bridge between like producers and consumers using the MySQL logging frameworks.
Carlos Malza, UC Santa Cruz. So Jeremy mentioned earlier the most important thing is that things are never get interrupted. So what is currently, and this is a really dumb question, and I'm sorry about my ignorance. When you push out changes, like patches to your production system, how much overhead is that? I mean, you have to stop things, you have to restart things. Can you say something about that?
Yeah, I can talk about that. So this goes back to the MySQL pool scanner I talked about. So it actually has automated upgrades and stuff built into it as well. So we can actually say upgrade this, and we have an upgrade the world. Where basically what it does, we talked about how we have like the 4 different data centers. So what we can basically do is we take down single instances within data centers, upgrade those, bring them back, and then we eventually fail around and so on and so forth. So it uses kind of the automated stuff we have for failure detection and handling to basically do the same thing, but in a controlled manner. In that way. So basically we can upgrade with theoretically without any downtime basically at all. There is a couple seconds downtime as you fail over masters. So when we're actually doing the master node, you have to change the master node, and there's a couple seconds there. But most things you won't even notice. It'll be like within refreshes and stuff like that.
And essentially, we had some major maintenance events, like things like upgrading switches in all the data center, or just when we had new version of Flash Cache, we had to rebuild every instance in the whole data center, and that would be kind of a project that might maybe run for a few weeks, but for someone else, that would be just essentially kind of throttling how many servers it wants to do, and that's just based on the health of the system. So massive maintenance actions is just as big as it used to be to migrate one server to another in our early days.
all about automation.
There's a question over there.
What is the impact of compression on query performance?
Again, we never really looked at the QPS performance of our systems. Our major focus is always how to have sustainable, like the thing in our databases, we have to fit the user data that is out there and allow the user accesses that are there. So we are not going to serve 20 Facebooks in a day. We have to serve one Facebook and we have to optimize for that. The query performance, it depends on obviously data distributions and so on. The way in the compression works, some of the data is uncompressed in memory, some of it is compressed. If your data is hitting disk, actually compression improves performance because it can cache more data in ODB buffer pool. If it's just purely in memory, it will slow down. So there are like all these different things that compression may add or remove. But for us, generally, compression has been a really successful story because besides actually improving performance, reducing IOPS in one place, reducing disk space in another place, we actually did not have much of performance problems. So we had to really work on making sure that the replication, the actual write operations became more expensive. And as they're a single thread, that was why we had a big focus on actually making it happen, making it work better and within our required performance levels. We don't really want to send 100,000 of queries to a few terabytes of data because that means we're doing something wrong with our application at that time.
Hi. I know you talked about link bench, but for these millions, billions queries per second, can you say something about the kinds of these queries? Reads, writes, single table, multi-table, rows?
So yeah, we gave the numbers before. So essentially, the data set that is being read is in 2 billion rows a second, and changes is just 10 million rows a second. So obviously, we're really read focused. Because most of these write operations that happen here, they're user generated. They're not just some click streams that happen out there. Of course, there is some metadata about certain, logging in or logging out. But it's really the graph access is it's Zipf distribution on association sets. These can be larger or smaller depending on age of user and so on. But it's Zipf distribution on object accesses. So the link bench though simulates the accesses that hit the data layer after the cache. We never really built a kind of full Facebook in-memory data store evaluation framework. It's just, our constraints are much more about shipping the data rather than just, running the QPS numbers.
So I think this is Domas Shrisha. So it's a related question probably, but you mentioned earlier that the caches are important, for the edge, and database is mostly important when you are hitting the disks. And yesterday, Michael Stonebreaker made a comment that everything is going to be an in-memory database. So do you see you going towards an in-memory database, or you actually see a totally different use case here?
If physicists give us cheap nuclear reactors, we may actually think about going in. No, it's the reality is we are running systems with the ratio of data to memory is increasing. If, I remember when I started, we were giving talks and saying, oh, if you hit 3-to-1 ratio, it's already pain, or 6-to-1. We can run systems 50-to-1 if we want. You cannot put, we are running commodity hardware, commodities, a bit mid-range server, but still it's 2-unit or 1.5 unit actually servers. And you cannot stuff that much memory in there. You cannot put that, the CPUs don't address that much memory as we need. And, a single 4 terabyte hard disk is, quite cheaper than 4 terabytes of RAM. And this cost difference for us is quite visible. We really, if we understand that we can store our data on disks, there is or whatever flash technology that is viable by cost. It's all these things are cheaper than putting it all into memory. And I really cannot understand how is it feasible to propose petabyte scale in-memory solution yet. If anyone is running in-memory petabyte solution, I don't know, maybe Exxon, they have big budgets, but we're we are, one of the major things I probably forgot to tell, our service is free for our users, right? It's like, they're not paying money. We cannot charge them. Like, look, we want $1,000 so we can put your data into memory. It's like, it's not working that way. We wouldn't get signups. We like our billion users.
OK, so one last question here, and we will switch to the next talk.
So agility was a big point yesterday. So you're very agile. Are you more conservative with things like schema changes because you have to roll that out and roll it back?
So the schema changes, there's a couple different things here. So one, we generally only do backwards compatible schema changes whenever possible. I can think of maybe on the once or twice we've ever done not backwards compatible ones. Just because you have the issue of software and databases all doing it at once. So like we take 2 weeks to change it. The software kind of has to evolve and understand the changing things as it's going on as well. And then the other thing we talked about is how a lot of the schema that our engineers see are actually it's application-defined schema. So they can very easily like add a new column that's not actually a column in the database itself, and so they're able to dynamically do their own whatever their needs are. And there's literally like thousands of those going on all the time, like where they say, okay, I need a new field for storing some new point of data about a user or whatever. And they can do those changes very easily and quickly themselves without even involving in doing actual schema changes.
We have like relatively easy meta schema management tools, but like in our data store, an object is usually a blob. And that blob is structured blob, but it's like all our frameworks around know how to parse those blobs, but like and adding a field is just simply adding a line of code somewhere and annotating it properly. So whenever someone reviews that, it's like, okay, you have schema change review. You don't really have to go and rebuild anything for that. Again, it's like in many of these cases, a schema change might be needed afterwards. Once you start understanding that this really is not the best design, maybe, but then you just do a migration to a more efficient model. And it's like we always allow our developers to like really iterate and have many pending projects, A/B testing. And like Ravi told that what we have from analytics perspective to drive these things, we also have to provide the very same way at the infrastructure level for anyone to experiment. And it's like sometimes people ask for a new table, but in most of cases they don't even need it. Like they can just unleash the data and eventually we'll figure out what to do with it. We have tools for that as well.
All right. Okay. Thank you very much.